Good morning, children. Right, we are moving ahead to irrational numbers, right, which is a part of real numbers chapters from your class 10 syllabus. Okay, we have already defined what rational numbers are. Any number which can be expressed in the form of p by q, where p and q are co-primes and q not equal to 0, then all those numbers are called rational numbers. We have also seen if it is in decimal point values, how to identify a rational number. So how to identify? The first category is if a decimal number which is terminating, then that is a rational number. And the second category is if it is not terminating, we have to check whether it is of a repeating kind, or that is recurring. So if the decimal number is non-terminating but recurring, then also that is a rational number. So then what are irrational numbers? See, when we define rational number, almost all the numbers, whatever we have studied till now, fall under rational numbers. That means all integers fall under rational numbers, whole numbers fall under rational numbers, natural numbers fall under rational numbers. So almost all the numbers, whatever we have discussed till now, fall under rational numbers. So then what are these irrational numbers? So irrational numbers are those which cannot be expressed in the form of p by q, which cannot be expressed in the form of p by q. And if it is in decimal values, if you want to identify the irrational number, then it should be non-terminating as well as non-recurring. It should be non-terminating as well as non-recurring. Such numbers we call as irrational numbers. Such numbers we call as irrational numbers. Usually, so when we talk about irrational numbers, root 2, root 3, root 15, of course root 5, pi, all these come under irrational numbers. Suppose if I say that some decimal value, if you want me to take 1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 1, 0. So such kind of things, even you have got something like in your problems also to identify whether rational number or not. Where 0 was there, like in the first two digits, between first two digits only 1 0 was there, then next afterwards a repetition of the same digit kind on only it appears, but one more 0 is added in between. Here you can see that ones are added in between. So these are all irrational numbers. These are all irrational numbers. So now when you talk about pi, see, it's very common that most of the people will get confused with this pi. So we always equate this pi to 22 by 7. You may say that, ma'am, now it is 22 by 7, which is expressed in the form of p by q. Then why is it falling under irrational number? Yes, there is a reason. Here pi is not absolutely equal to 22 by 7, but it is nearly equal to 22 by 7. Whatever we are taking in problems, whenever you are substituting 22 by 7 in place of pi, right, we are neglecting certain values and taking only the approximate value but not the actual value, where actual value of pi is non-terminating and non-recurring kind. So thus pi is also an irrational number. Pi is also an irrational number. So please remember, if suppose in your board examination 22 by 7 is asked, then it is a rational number. If pi is asked, then it is irrational number. Please remember, children. So there you should not lose your half mark. Okay, right. So this is how we define irrational numbers. Irrational numbers are those numbers which are not rational. Right. So then non-rational real numbers are irrational numbers. And examples we have given here: root 2, root 3, root 15, root 5, pi, etc. So these are all irrational numbers. Clear? Right. So now we have some theorem based on which we are going to prove few things to be irrational. So what is this theorem? Theorem 1.6. What does it state? Let p be a prime number if p divides a square. A is a positive integer. Suppose if a is a positive integer and p is a prime number, which divides a square, then P divides also A. This is what which we are going to prove as well as discuss about the theorem. So what is that? We are taking P as a prime number and A is any positive integer. Suppose if P is dividing A square, then it implies that P also divides A. P also divides A. So now let us see how to prove that. Okay, so let us take the proof part. So now let us suppose that some A is a positive integer, and according to the previous theorems, we have already seen that from prime factorization as well as from previous knowledge, A can be expressed as the product of its prime factors, and those prime factors are unique. This also we know, we have defined it. So therefore I define A as a product of prime factors P1, P2, P3, etc. till Pn. So we don't know what A is, we don't know what P1, P2, P3, but we know one thing: A is a positive integer where A can be expressed as product of its prime factors. Suppose if you take 8, if I ask you to define it as like a product of its prime factors, what are the prime factors you have there? 2 into 2 into 2 is not 2 cube. You will write it as 2 cube, but you can't write it as 2 into 4 because 4 is not a prime number. 4 is a composite number. Thus, I am defining here A as a positive integer, and P1, P2, P3, etc. Pn are prime factors of A, and these are unique. You can't have different kinds of prime factors, right? So whenever you are reducing a number into its prime factors, the prime factors are going to be unique. So these are the unique prime factors that A is having. Right. So therefore, when I define A as P1 into P2 into P3, etc. Pn, so then now A square will be, then A square will be equal to P1, P2, P3, etc. Pn multiplied by again P1, P2, P3, etc. Pn. Is it not? Yes, A multiplied by A is A square. A multiplied by A is A square. So now what is that we have to prove here is that P divides A square is given. So now therefore from fundamental theorem of arithmetic, it follows that P is one of the prime factors of A square. Yes or no? So what is given, we'll write. So given P divides A square implies P is one of the prime factors of A. Prime factors of A, is it not? So when he says that P is a prime number, in the theorem what did we consider? P is a prime number which divides A square. So therefore, if P divides A square, obviously P is one of the prime factors of A. Yes, then fantastic. So if that is the case, you have the uniqueness condition also, is it not? So the theorem of fundamental theorem of arithmetic, according to it, whatever the prime factors you have, they are unique. So therefore, P can be any one of P1, P2, P3, P4, etc. Is it not? P cannot be anything different from this. P cannot be anything different from this. So therefore, from uniqueness of fundamental theorem of arithmetic. So what can we write? P can be anything from P1, P2, P3, etc. Pn. Is it not? So it could be anything, because unique prime factors we have. So p can take any one of these values. We don't know whichever value may be equal to p, but it can take the values from p1, p2, p3. So when you say that p is any one of these, then obviously these are the factors of a, yes or no? So implies P is a factor of A, is a factor of A, which means that P divides A. Hence proved. Hence proved. Okay, so let's discuss the theorem again. So now let P be a prime number. If P divides A square, so what is given? P is dividing A square is given. A is any positive integer. Then what is that it which implies P also divides A. P divides also A. So now since A is a positive integer, I am writing it in terms of I factorized into its unique prime factors, right? P1, P2, P3, etc. Pn. So it's a product of all these prime factors. Now if A is this, then what is A square? A square is equal to this multiplied by this again, is it not? But what is given? P divides A square is given. That means P is one of the prime factors of A. Yes or no? That means P can take any one value out of P1, P2, P3, Pn and etc. Yes, if suppose that is from the uniqueness of fundamental theorem, it can take P1, P2, P3, any value. If it is taking any one of these values, what are these values? We have considered these values are the prime factors of A. So thus P also divides A. When P is a factor of A, it implies that P divides also A. Hence proved. So this is the theorem. So just pause the video for a moment and copy down these things. Irrational numbers, numbers which are not rational are called irrational numbers. Examples are given here. Okay, then the theorem statement, theorem 1.6. You can take the screenshots. And this is the proof part. Right. Okay, pause the video, take the screenshot and then. So now let us go by to show that root 2 is irrational. So here we are going to prove it using whatever theorems we have learnt till now. We are not going to find out root 2 value and say that yeah, it is non-terminating and non-repeating, therefore it is irrational. It is not that way. Neither we are going to take a calculator and find the value of the root 2 and say that yeah, it is non-repeating and terminating, so therefore it is irrational. No. So we are going to prove it. So which method? That is called proof by contradiction method. Contradiction method means we are going to assume something and then finally we are going to prove that whatever we have assumed is not true. That means it is contradicting our assumptions, like that. This is called contradiction method. So therefore in this method what we are going to do is like we are going to use the Euclidean lemma and then as well as the fundamental theorem of uniqueness of the factors that any number can have. So using these two we are going to prove that root 2 is irrational. Okay, so now let us see the solution part. So let us assume first of all root 2 is rational. Okay, let us assume that root 2 is rational. What are we assuming? We are taking root 2 to be rational. We are taking root 2 to be rational. And then finally what we are going to prove? That whatever we have assumed is wrong. Therefore root 2 is irrational. Okay, did you get the point why we call this as contradiction method? Yes. So now since we have assumed root 2 as a rational number, then root 2 should be expressed as something like root 2 is equal to a by b. Yes or no? Because any rational number should be expressed in the form of p by q, where p and q are co-primes. So now here a and b are where a and b are co-primes. Co-primes means they should not have any other factor other than 1 in common. In common. That means whichever one particular number is dividing A should not divide B again. Or whichever number which is dividing B should not divide A. If suppose if a number can divide both A and B, it means that it is having a common factor other than 1. That means co-primes. So they are not co-primes. When they are not co-primes, it can't be expressed in the form of A by B. Root 2 cannot be. If root 2 cannot be expressed in this form, it means that root 2 is not rational. If it is not rational, means it is going to be irrational. This is the line of thinking or the proof that we have to make. So therefore, we have assumed that root 2 is A by B, where A and B are co-primes. Okay, so now since if this is the condition, then A can be expressed as A is equal to B root 2, is not cross multiplication. A is equal to B root 2. Or now squaring on both sides. You have A square is equal to 2B square. You have A square is equal to 2B square. It is something that A square is a number, B square is a number, and it is 2. It is 2 here. Now see, compare this with Euclidean lemma, Euclidean division lemma. So it is something that a number, right? Some A which is expressed as BQ plus something R, where R being 0 here. That means when the remainder here is 0, which implies that 2 absolutely divides A square, is it not? Which implies that 2 divides A square. So 2 is a factor of A square. 2 is one of the factors of A square. This is what we have come to a conclusion from this one. Yes. So now from the previous theorem, that is theorem 1.6, we have seen that if a particular number, if a prime number, especially 2 is of course a prime number, if a prime number divides A square, then P also divides A, is it not? So therefore, now from theorem 1.6, if 2 divides A square, then 2 divides A also. So therefore what you can say that therefore 2 is a factor of A. Very good. 2 is a factor of A. So now this is from Euclidean lemma you are able to say, is it not, that 2 divides A square. Now whenever, that is from theorem 1 point, that is from Euclid's division lemma. So you can write this one. Right. So therefore 2 is a factor of A. Now since 2 is a factor of A, I can write in any manner, like so that A is equal to, right? So A is equal to 2C. So for some integer C. See, you said that 2 can divide A, is it not? So again from Euclid's lemma, what A can be expressed as 2 times of some quotient plus remainder. Here remainder is 0. We are taking the remainder to be 0 here because 2 divides A absolutely. So therefore A can be expressed as 2C, is it not? A can be expressed as 2C. So therefore now substituting this A in place of this one. Substituting this A in place of A square is equal to 2B square. Right? So let me write this as equation 1. So substituting A is equal to 2C in equation 1. We get, what do we get? So in place of A square, you are taking 2C whole square is equal to 2B square. So what do we have? 4C square is equal to B square. So now that is again This is 2 times. So 2c square is equal to b square. Let me do it here. Okay. Or b square is equal to 2c square. See how the equation has converted. Now here previously you have expressed a square is equal to 2b square. A square is a number. B square is some quotient. So 2 is the divisor. 2 is dividing a perfectly without leaving any remainder here. So similarly, here 2 can also divide b square and leaving a remainder to be 0. That means which implies that 2 divides b square and also 2 divides b, is not 2 divides b from theorem 1.6. So therefore what is that now? 2 divides b as well as 2 divides a, which means that 2 is a common factor of a and b, implies 2 is common factor of a and b, implies a and b are non-coprime. A and b are not coprime. Therefore root 2 is irrational. So therefore whatever we have assumed is wrong, hence root 2 is irrational. This is how you are going to prove. Okay, is that clear? So I'll explain this once again. So what is the condition that you are going to get? Proof by contradiction method. So the example problem here is to show that root 2 is irrational. So what did we assume? We assumed that root 2 is rational. So when root 2 is rational, you should express it in the form of p by q. So I took it as a by b, where a and b are co-primes. That means a and b should not have any common factor other than 1. So since they are like root 2 is a by b, a can be expressed as b root 2. And squaring on both sides, you have a square is equal to 2b square. Now, from Euclid's lemma, we can easily say that 2 divides a square. So, without leaving a remainder. And then now from the theorem 1.6, if at all a 2 divides a square, 2 also divides a. So, 2 is a factor of a. And since 2 is a factor of a, I can write a is equal to 2c. C could be the quotient without leaving a remainder. See, there should be a difference. See, here it is a square is taken. So, you are writing 2b square. Here a is taken. So, a is equal to some multiple 2c. So for some integer c. Therefore, a is equal to 2c, and substituting this in the first equation, you can prove that b square is equal to 2c square, which implies that 2 divides b square also as well as 2 divides b. That means 2 is the one which is a common factor of both a and b, which shows that they are not co-prime. That means root 2 is not rational, which means root 2 is irrational. This is how we have proved that root 2 is irrational. Okay, children. So pause the video for a moment and then take the screenshot. Proofs are very, very important. And also follow whatever I have given here. The same kind of steps. Don't follow your textbook for this proof. And then the last part. So with this we'll conclude today's topic. So please try to understand the logic behind how to prove that a particular number is irrational. That is very, very important. Okay, see you in the next class.